All right, here is section 3.5. This is the last section out of chapter 3, exponential functions, logarithmic functions and their properties. We're going to be solving some more exponential and logarithmic functions, obviously. So let's get started. This is a refresher. The equivalence property says if I have the same base on both sides, and the base is raised on each side, each base has an exponent, then the exponents are equal. So these two problems you have seen already, but just a reminder, just to refresh your memory in case it's been a minute. We have 3 raised to the x plus 5 is equal to 81, and the property I want to use is the equivalence property of exponential expressions. So that means I need the same base. 3 is going to be the base that I like, because 81 can be rewritten as 3 to the 4th. In the previous video we did 81 is 9 squared, 9 is 3 squared, so we ended up with 3 squared, power to power raise power to a power, and you multiply. So I have two bases that are bases that are the same, so this means their exponents must be equal. So that means x plus 5 has to equal 4, which means x equals -1. Subtract 5 from both sides, x is -1. And then we want to check. And the way you check is you go back to the original, plug in, and see if you get equality. 3 to the x plus 5 is equal to 81. X is -1. -1 plus 5 is 4. 3 to the 4th is 81. 81 is 81. That checks. So that means my solution set contains -1. Be careful when you're doing these. I still get tempted to put 81 as my answer when in fact I'm going after what I checked for x, not what I get at the end of that check. Next, same concept, starting out, I have 5 to the x squared plus 8 is equal to 125 raised to the 2x. I need the same base because that's the property I'm using. And 125 is 5 cubed. 5 times 5 is 25. 25 times 5 is 125. Raise a power to a power on the right. And I get 3 times 2x is 6x. And then, now that I have the same base, the rule says that x squared plus 8 must equal 6x, which means x squared minus 6x plus 8 is 0. If you get there and get stuck, remember what kind of equation you have, right? On the previous problem, this was linear, so just get x on the side by itself. This one's quadratic, so that means everything goes to one side, and then we try to factor. Two numbers that multiply to positive 8 and add to negative 6. We know both those numbers have to be negative because they've multiplied to a positive but added to a negative. Those are 4 and 2. By the zero product principle, I know that if two things multiply to 0, one of them is 0. So x is 4, x is 2. Now we're going to check. And let me show you a quick way to do this. You can absolutely do this by hand for these problems. Just trying to run some stuff off the screen here. I'm going to put, let's get rid of these for a second because they're just confusing. If I put f of x is equal to the left-hand side of the equation, f of x is equal to, let's remember the problem, f of x is 5 raised to the x squared plus 8. And then g of x is equal to 125 to the 2x. And they have added some feature in Desmos where if you don't put parentheses, if you have a second keystroke, it assumes you mean to go down. So that's why you see me do parentheses here. You may not have seen those before. Now, I know I'm correct. I know this checks if when I plug in my solution, that F and G give me the same return, give me the same value. So my two solutions were 2. So I'm going to plug it into the left-hand side, plug it into the right-hand side. They match. And then the other possible solution was 4. And they both do. Okay, let's drop this in. Again, I know this is, you've seen this problem and this process done before. That is okay. It's not a bad thing to be repetitive sometimes in math. And here's all of our work. And this is our check. Work. Left and right equaled when x is 2. Left and right are equal when x is 4. So that means my solution set contains both 2 and 4. Let's get rid of all these little words here. Contains 2 and 4. Now, the equation you haven't seen before is 6 to the x is equal to 350. And this is what's the nice way to say it? It's a bit of a stretch, but I want you to be introduced to it. I have a log. What I have down here is an exponential. 6 to the x is equal to 350. Your calculator cannot do that problem, okay? But this is an exponential form, so I'm going to rewrite this in logarithmic. Rewrite in log form. So remember the rules. Remember my conversion here. B to the x is equal to a corresponds to log base b of a equals x, right? What power do I raise b to get a? So that means I can swap out 6 to the x is equal to 350 as log base 6 of, and then what is it? A is the 350 equals x. Now, your calculator cannot do this problem either, because unless you have an advanced calculator that does different bases, the calculator only has the common log and the natural log. So I can't solve this directly. So what do? I have a log base 6 of 350. What power do I raise 6 to get 350? I use the change of base form to rewrite this in terms that my calculator can deal with. Change of base says if you have log base b of x, this is equivalent to log base a of x divided by log base a of b. Look at what happened here. The base went from whatever the base was when I started to a. I get to pick a as long as a is not 1. And what happened? The argument x is in the numerator, and the argument, which is the old base, is in the denominator. Okay? So if I'm doing these, I want it to be any base, a base that I want so that I can do this problem on a calculator. I'm going to want a to either be 10 or e. Right? I'm either want to use the common log or the natural log. And what we'll typically do is use the natural log because it's 2 characters to write instead of 3. There's really no other explanation for it. So that means, I'm going to rearrange, just swap sides here, and then write out what we want. If x is equal to the log base 6 of 350, That means I can rewrite this as the natural log of the argument, which is 350, divided by the natural log of the base, which is 6. And that's how you use the change of base formula. If you're doing it by hand, if you pop that in, this is something you can now do on the calculator, whereas before, log base 6 of 350 equals x cannot be solved on the calculator. If you want to check, you're absolutely welcome to. Again, I would strongly recommend using Desmos here rather than doing 6 raised to the natural log of 350 divided by the natural log of 6, because that could get messy pretty quick. But this solution works, and that's what we care about. So first page done. And now we're going to go on to solving exponential equations using logs. All right. Now, we haven't seen this before. Everything we've done up to this point has been get the same base so that your arguments are equal, or get the same logs so that your arguments are equal. Now we're going to do a process. All right. Do not let this freak you out, but I'm going to tell you this is the most intense part of 3-5. Okay. And you're going to be using all of the rules that you can come up with to get this work done. Here's the first step. What is the goal? The goal is to solve for x. All right? X is currently in the exponent. Okay? I can't do anything with it until I get it down. So the only way to get it down is to use the properties of logs. Remember the power rule? Power rule says if I take the log, and that's just any log, of b raised to the a, I get to rewrite that as a times the log of b. Remember that power rule? This is my goal. I want to get this equation so that one side has the base raised to a power, and that power contains x. So in this one, first up is isolate the exponential expression. Where's the exponential expression? It's e to the 0.4x. Well, that means I don't need this 2 over here because it's just being bothersome. So let's get rid of it by subtracting it from both sides. Negative 3e to the 0.4x is equal to negative 7 minus 2 more is negative 9. And then I want the e to the 0.4x by itself. It's currently being multiplied by negative 3. So I'm going to divide both sides by negative 3. And now I have e to the 0.4x is equal to negative 9 divided by negative 3 is 3. All right. And now what? What can I do now? Well, I have exponential notation, but instead of using it, instead of doing what we did on the last problem, what I'm going to do is remember that my goal is to solve for x. And in order to solve for x, I've isolated, and then the second step is take the logarithm of the same base on both sides of the equation. This is typically the natural log. Okay, that you'll see me use that exclusively. So the next step, step 1 is done. Isolate the exponential expression. Step 2, take the natural log of both sides. So that means the natural log of e, let's not use red since I've been using red to show progress. There's step 2. Here's step 1. Natural log of e to the 0.4x is equal to the natural log of 3. And then the power rule. The whole goal of this is this step. 0.4x times the natural log of e is equal to the natural log of 3. All right. Now, natural log of e, remember natural log is log base e, so log base e of e is 1. So that means I have what? Let's scoot over. That's 0.4x is equal to the natural log of 3. X is almost by itself. Okay. And then, so what do we do? That was step 2. This is step 3 when I brought the power down. And then step 4, solve the resulting equation. X is currently multiplied by 4/10. I would like it to be by itself. So divide both sides by 0.4. And I come to the result that x is equal to the natural log of 3 divided by 0.4. If you're getting your calculator out now, to get that into a decimal, stop yourself, hold on tight, leave this as natural log of 3 divided by 0.4. This is called an exact answer. And we love exact answers. All right. Natural log of 3 divided by 4/10 is exact. If you take the natural log of 3, you're going to end up with a number that most likely continues forever, or has more numbers than we're going to keep, which means you'll round. And in these problems, if you take that exact answer and round it and then plug it back into the original, see if it works, it'll never work, because you'll never be able to hold on to all the decimal places that result from taking any log of a number, almost any log of a number. But anyway, there's my exact answer. If you want to check, again, Desmos is a great tool for this. You can check this by hand as well. Let's change it. So f of x is 2 minus 3 e to the 0.4x. And g of x is the other side of the equation, which is -7. That's very boring, right? So g of x is -7. That's just a horizontal line. So what did we say my solution was? My solution was the natural log of 3 divided by 4/10. And then for g of x, I plugged in the same x. If you're looking at me and saying, hey, I could have told you it was going to be -7 because the whole right side is -7. It's just doesn't matter what x is. You get -7. You're absolutely right. Okay. If you didn't catch that idea, then that's why we when we teach something in math, we try to make sure that the rule sticks for all possible cases. And in this one, plug the left-hand side of the original equation into f of x, plug the right-hand side into g of x, and then take the answer you found and then plug it in as the arguments for f and g. If f and g give you the same result, that is a solution. If f and g do not give you the same result, it is an extraneous solution, which means we do not count it. Those typically result from unknowingly dividing by 0 or leading to, there's a step in algebra that makes the argument of a log negative, that kind of stuff. So what's my solution set look like? Again, fight the urge to pick up the calculator. Leave this alone. Do not round. Solution set is natural log of 3 divided by 4/10 x. And then this is the check in Desmos. All right, so next we have x is in the exponent, is in two different exponential expressions. Let me make sure my vocabulary is right. Exponential expression on the left is 2 raised to the x minus 5. Exponential expression on the right is 0.75 raised to the x. Both of those are exponential expressions, and then when we put the equal sign between them, it's an exponential equation. So when I say the first step of the process says to isolate the exponential equation on one side, there's a variable in both. So I've got two of them. That's okay. So what we'll do is if I cannot isolate it, I am going to leave them on opposite sides for now, because the second step is take the natural log, or take a log of both sides, because the goal is to get x down. So I'm going to take the natural log of both sides, remembering the point and purpose of this is use the power rule to bring down the exponent, and then it ends up happening on both sides. All right, now the next thing is I'm going to get x, and then the problem says solve, right? Get x by itself. I want you to take just a little note here. Okay. I never want to see you take natural log of 2 here, plug it into a calculator, and get a decimal. I want it to say natural log of 2 so that I have an exact answer at the end. Same thing on the right. But these are just numbers, right? So natural log of 2 is a number. Natural log of 0.75 is a number. So to make life easier, I'm going to let the natural log of 2 equal a. Actually, I'm going to do c and d, so because a and b have been thrown around. I'm going to let natural log of 2 be c, and I'm going to let the natural log of 0.75 be d. Why would I do that? Well, the algebra that we have to do to solve this, if you're not comfortable with natural logs or you haven't used them, it's very easy to lose one because of the way the notation works and because of the parentheses that get used. So what I'm doing is I'm just going to swap this out. So x minus 5 times c is equal to x times d. Distribute on the left, cx minus 5c is equal to dx. That is the exact same expression, or the exact same equation up above, but it's simplified. It's all those natural logs have been taken out, everything's been distributed, and that makes, to me, it makes it a lot easier. So I have x's on both sides, so I want to get everything with an x on one side. So let's do that by subtracting c of x from both sides. And that means I now have c of x minus c of x is 0, negative 5c is still on the left-hand side, and then on the right I have d of x minus c of x. All right. Now everything with an x is on one side, everything without's on the other. My goal is to get x by itself, so on the right-hand side, all of the terms have an x, which means I can factor out that x. Right? D of x minus c of x, both of those have x's in them, so I bring the x out front. And I want x by itself. X is currently multiplied by d minus c. Well, how do I get rid of it? If x is multiplied by something, I divide both sides by it. And I now end up with x is equal to negative 5c over d minus c. Now, let's resubstitute. Natural log, what is it? C is natural log of 2. And d is the natural log of 0.75. So my problem, x is equal to negative 5c over d minus c becomes negative 5 times the natural log of 2 divided by d, which is the natural log of 0.75, minus c, which is the natural log of 2. And that is my answer. Okay? The little thing I did at the beginning there where I let natural log of 2 be a number and d be, or let natural log of 2 be c and let natural log of 0.75 be d, what that did is it just replaced all the math I just did, which none of this was difficult. Get all the x's on one side, factor out an x if you have multiple terms with x in it, and then divide by whatever's left over after the factoring. That's all good and fine. We're good there. But doing this step, what it did is it made it where these steps don't have -5 natural log of 2 is equal to natural log of 0.75 times x minus natural log of 2 times x, right? We just replaced them with just letters. We came back, we resubstituted them, and everybody is happy. All right, so there's my solution. Does it work? Again, this is where Desmos is going to help. So left-hand side, 2 raised to the x minus 5. Right-hand side, 0.75 raised to the x. And then take my answer, 5, and I'm going to do parenthesis here just so the computer doesn't get confused. 5 natural log of 2 divided by natural log 0.75 minus natural log of 2. I've told you in the past, I was trained by a lot of times when I want to go back and look at my mathematical tendencies, I always put parentheses even when you're taking a log of a single number. It's just because, again, I was trained by a guy who loved calculators. So I don't want to type that again, so I'm just going to hit copy and paste. Did it work? Yeah, it checks. So let's grab that screen clipping to prove our work. And then this is the check. In Desmos. So my solution set consists of -5 natural log of 2 divided by natural log of 0.75 minus natural log of 2. All right.